Okay, everybody, this is it. Chapter 20, carboxylic acids and their derivatives. So what it means by carboxylic acids and their derivatives is that we're going to discuss carboxylic acids, esters, nitriles, acid chlorides, acid anhydrides. So there's a few different functional groups that show up in this chapter. And we're going to start by looking at carboxylic acids. But before we do that, I want to do something that I've done a couple other chapters this semester. As you can see, there's a lot of slides in this chapter. And once we get to the very end, and I'll have to figure out exactly where it is, but yeah, so in this chapter, we cover a lot of new reactions, okay? There are many, many, many new reactions. So like I said, some of the functional groups that we're going to see are going to be carboxylic acids, of course, and then we're going to see acid chlorides, acid anhydrides, esters. I mentioned nitriles. I forgot amides, so amides are in here. And so you can see that there are some similarities in some of the reactions here, and there's plenty of nuances as well. So like I said, there's a lot of new chemistry in this chapter, but do not be intimidated. You won't be the first person to study it, and you definitely won't be the last either. So a lot of new reactions. And also, just to put this bug in your ear, this chapter is very nomenclature heavy. And the reason why is because we talk about the nomenclature of each one of these groups. So we talk about nomenclature of carboxylic acids, acid chlorides, acid anhydrides, esters, amides, and nitriles. They're all covered in this chapter. So lots of reactions and lots of nomenclature. Well, with that in mind, let's get into it and look at carboxylic acids by way of these structures here, which give us a little introduction. It says carboxylic acids are very abundant in nature. They're found in a whole bunch of naturally occurring compounds as well as pharmaceuticals. And if you just look at a few of them here, I know you all know acetic acid because this came up Avogadro's number of times in general chemistry too. It's used as a weak acid in that class, and you learn about Ka. And it's responsible for the smell, the pungent smell of vinegar. And so it's the acid that's found in vinegar. Then you go to butanoic acid. It's responsible for the odor of sour butter. And this is not to be, you know, what's the word I'm looking for? Facetious or anything like that. But butanoic acid is the smell of vomit. So I'm sure everybody smelled vomit before. So that's what it comes from. You can see the odor of dirty socks comes from hexanoic acid. And I'm sure you've all heard of lactic acid before, right? You've all studied anaerobic oxidation, glucose. You've heard of, lactate fermentation and all that kind of stuff in your biology classes. But when milk goes sour, what you get is you get lactic acid. Anyhow, so you've also probably all heard of aspirin before. So this is the structure of aspirin down here. So this is acetyl salicylic acid. And yeah, what else? We got here a TB drug, and then we have another compound here that's used for the treatment of acne. So we find carboxylic acids all over the place. And as going back to the whole acetic acid thing, so the United States produces a lot of acetic acid every year, and most of that is used to make vinyl acetate. So this molecule here is called vinyl acetate. So the vinyl group is this portion, right? That's a vinyl group. And then the acetate, you should know acetate. Acetate is this portion right here. So vinyl acetate is used in paints and adhesives. So if you've ever gone to the paint store, the paint will have some vinyl acetate in it. And so carboxylic acid derivatives are hugely important in organic chemistry. And that's why we spend so much time studying them in this class. Now, we're going to spend quite a bit of time in this chapter just looking at nomenclature of carboxylic acids and their derivatives. And something that I don't really bring up a ton in Organic 1 or Organic 2 at the non-majors level is the priority of functional groups, or what we call the hierarchy or the priority of functional groups. Anyhow, this is something that's shown in the appendix of our textbook. And you can see that if you look at all the different functional groups, the carboxylic acid is actually the king of the castle, okay? It's one of the highest priority functional groups. So if you have a compound that has both a hydroxyl group in it and a carboxyl group in it, the carboxylic acid is going to take priority. And so the question is, would you call this compound an alcohol, or would you call this compound a carboxylic acid? The answer is you'd call it a carboxylic acid, okay? And when we have two functional groups in a compound, like we have here with this 5-hydroxy 4,4-dimethyl pentanoic acid, we don't look at many bifunctional compounds in this class, but it is worth knowing that the carboxylic acid is one of the groups that's at the very top. All right. Another point that's important from this slide here is that, let's say we have a compound like butanoic acid, and of course you have to know how to name this compound. We don't call this one butanoic acid, right? The carbonyl carbon is assigned number 1, 2, 3, 4, but we don't have to give it a number 1 because the carboxylic acid carbonyl, that carbon is assigned position number 1. So it would be redundant to call this one butanoic acid, okay? There's no point in doing that. Now, if you have your carboxylic acid group attached to a ring, what you do is you use the suffix carboxylic acid, and then you just name the ring. So you'd say cyclohexane carboxylic acid, right? If you had this molecule here, right? Let's say you drew a cyclopentane, and then you put a carboxylic acid, and you should know that the condensed form is CO2H. You would call this cyclopentane carboxylic acid, right? Cyclobutane carboxylic acid, et cetera, et cetera. Also, I think it's important for you to know the names or the common names of the first 5 carboxylic acids. So the first one where you have 1 carbon is formic acid. Number 2 is acetic acid. Number 3 carbons is propionic acid. 4 carbons is butyric acid, and 5 carbons, so that's 1, 2, 3, 4, 5. This one is called valeric acid. So valeric acid. And if you took the time to remember the first 5 common aldehydes, then you'd see that it's not much of a stretch to go from the aldehyde to the carboxylic acid, right? You had formaldehyde, formic acid, acetaldehyde, acetic acid, propionaldehyde, propionic acid, butyraldehyde, butyric acid, and valeraldehyde, we get valeric acid, right? And of course, these compounds also have systematic names, right? 1 carbon, this would be methanoic acid. So formic acid is also methanoic acid, right? 2 carbons would be ethanoic acid, propanoic acid, butanoic acid, and pentanoic acid. And then, of course, benzoic acid. I'm sure that some of you recrystallized this compound in the spring with me. If you took 3102 with me, I'm sure somebody who's hearing the sound of my voice did a recrystallization of this compound. And the reason why we get students to recrystallize this compound is because it works really, really well. And this compound is going to come up a bunch of times in the class, so you should know the common name of benzoic acid. In fact, I think I asked you to memorize this back in chapter 18. Okay, so let's move on from there. There's also some dicarboxylic acids that you should know. And, you know, why I think these are so pertinent for us is, first of all, they're common, right? We use them all the time as organic chemists. But also, these are found all the time, I shouldn't say all the time, but we see these dicarboxylic acids in biochemistry, right? You've probably heard of succinate or oxalate. You know, so if you studied the Krebs cycle, you might have seen some of these carboxylic acids. So if we have, let's say, 5 carbons, we'd call that pentane dioic acid. If you have 2 carbons, like an oxalic acid, you call this ethane dioic acid. And then you'd call this propane dioic acid, then butane dioic acid, right? And then here, of course, we have 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5. So these 2 are the same here. But you should also know the common name. So if you have 2 carbons, it's oxalic acid. 3 carbons is malonic acid. 4 carbons is succinic, and 5 carbons is glutaric. And the way that my students taught me to remember this, because when you have 6 carbons, and let me just scribble it in here quickly. If you have 6 carbons, the 1, 2, 3, 4, 5, 6, this compound would be hexane dioic acid, hexane dioic acid, or the common name is adipic acid. So the way my students taught me to remember this is, oh my stars, go away, go away. That's, and again, they taught me that years ago. So, oh my stars, go away. All right. In fact, that was the first class I ever taught at UCCS. They taught me, oh my stars, go away, for oxalic, malonic, succinic, glutaric, and adipic. So one of my students says in the chat, incredible. Yes. Okay. It was the first class I ever taught. That's what they came up with. They were also the class that taught me that when you look at a Fisher projection, the horizontal bonds, it's as if they were coming up to give you a hug. And I just said, that's incredible. I've been studying this for years and I never thought of that. So I thought that was pretty brilliant of them to think of that. Anyway, there you go. So some carboxylic acids and some dicarboxylic acids that you need to know. So with all that in mind, let's see if we can tackle this problem here. Give it the old college try. Got a few of them here. It says provide an IUPAC name and a common name for each of the following compounds. So this one, I'm going to draw out the whole structure here. So we've got a carboxyl group. Then we've got a total of what? 5 carbons. So 1, 2, 3, 4, 5. So we'd call this pentane dioic acid, right? That would be the systematic name or the IUPAC name. Could anybody come up with a common name of this one? You might have to go back a slide. Common name, anybody? 5 carbons. Oh my, so it's oh my stars, go. What is the G? Glutaric acid. Thanks, Maria. Yep. Glutaric acid. All right, good. The next one, I'll draw the structure right here. So we've got a total of 1, 2, 3, 4 carbons. So let's see here, 1, 2, 3, 4. And so the IUPAC, or the systematic name, would be butanoic acid. And then the common name is pretty close. It's butyric acid. I realize that can get a little frustrating, but you do have to know the two. And then the last one, hopefully you recognize that when you see C6H5, that's the same thing as a phenyl. So this would be phenyl CH2OH. So this is benzoic acid, right? So that's this compound, right? This compound. Now, I would only ever use the common name of this compound, which is benzoic acid. But it did teach you that if you have a ring, you can just name the ring and then say carboxylic acid. And so technically this would be benzene carboxylic acid. It's one of those names, though, that if somebody said that to me, like if Mr. Mayer said that to me in the lab, where's the benzene carboxylic acid? I'd say, have you been drinking or something before you came to work? Anyhow, so it's a joke. But yeah, it's just something that nobody would ever say, kind of thing. All right, next one. Students usually like these problems where I give you a name and then you just draw the compound. So the first one is cyclobutane carboxylic acid. So we'll start by drawing a cyclobutane. So that's just a square like that. All right, and then carboxylic acid. We just put our carboxyl group on here. So there we go. And something like this, and we're done. Oops, that doesn't look very pretty. There we go. The next one is 3,3-dichlorobutyric acid. So let's see here. We've got 1, 2, 3, 4. So there's our butyric acid. And then, of course, this is carbon 1, 2, 3, 4. So on carbon 3, we've got 2 chlorines. So we'll scribble those in like so. The next one is a glutaric acid, right? And you told me a few seconds ago that glutaric acid has a total of 5 carbons in the parent. So let's write this down. So 3,3-dimethyl glutaric acid. So let's see here. Oops, that's a pretty ugly bond. Let me fix that. There we go. So we've got, let's see, 1, 2, 3, 4, 5. Go. And then it's 3,3-dimethyl. There you go. Give me a thumbs up if you follow me on those ones. Or stop me if you have a question on any of the nomenclature. Usually students are pretty rock solid on these ones. And let's try these ones. So come up with a IUPAC name. You can see the last one's an amino acid. Anyhow, so let's see here. We'll find the parent chain. So 1, 2, 3, 4, 5, 6. So this is some kind of hexanoic acid. So we can scribble that in here, hexanoic acid. We've got 4 methyl groups, 3,3,4,4 tetramethyl. So 3,3,4,4 tetramethyl hexanoic acid. Beautiful. There we go. That's pretty good. All right. The next one. How many carbons are in the parent of the next one? Anybody? How many carbons would be in the parent? And you can see their symmetry in the molecule, but I think there's 5, right? So you'd start here, right? You'd start 1, 2, 3, 4, 5, right? And then you have this propyl group dangling off here. Yeah. Okay, good, good. All right. So we've got some kind of pentanoic acid, pentanoic acid, and then we've got a 2 propyl. So we'll scribble that down, 2 propyl. All right. They didn't ask us to give a common name for this, but we could. And can I just show you something interesting about the common names? So if you want to give this a common name, the way we do it for the substituent is you start with a carbon after the carbonyl, and you call that the alpha carbon. So this is alpha, beta, gamma, and then delta here. And so you'd say alpha propyl. You'd say alpha propyl, propyl valeric acid, like that. And then the next one, oh boy, we've got a phenyl group. We've got all kinds of stuff going on here. So first of all, we've got 1, 2, 3. So this is 2 amino, 3 phenyl propanoic acid. So let's scribble that down. So 2 amino, 3 phenyl propanoic acid. Did anybody figure out if this is an R compound or an S compound? Anybody figure this one out? All right, we've got our proton going in the back. Thanks, Tiana. I think you're right. So we have the nitrogen as being number 1. This is 2. This is 4. This is 3. So we go 1, 2, 3. So yes, it's an S compound. So we have S, 2 amino, 3 phenylpropanoic acid. And when you enroll in biochemistry, so in biochem, you'll have to memorize the name of this compound. This is L-phenylalanine. Phenylalanine. All right. One of the first things you have to do in biochemistry is memorize the 20 naturally occurring carboxylic acids, and phenylalanine is one of them. There we go. Hot dog, we have a wiener. Let's move on to section 20.3, where we talk a little bit more about structure and properties of carboxylic acids. There should be nothing new to you in here. This should be kind of old hat, but it bears repeating some of the concepts here. Hopefully you remember that the carbonyl carbon is sp2 hybridized, and therefore it is trigonal planar, right? It's flat as a pancake, and that's going to be pertinent when we look at nucleophilic attack on a carboxyl group or a derivative of a carboxyl group. And then you should also remember this, that you can have extensive hydrogen bonding between 2 carboxylic acids, because they can kind of form this, what we call a dimer here. And so that's why carboxylic acids have very high boiling points. So higher boiling points than alcohols. So if you were to compare something like ethanol versus, ethanoic acid or acetic acid, the carboxylic acid is going to have a higher boiling point, all right, because it can do even more hydrogen bonding. The boiling point of acetic acid is somewhere around 118 degrees Celsius, the boiling point, and the boiling point of ethanol, you probably know, is 78 degrees Celsius. So anyhow, just a little food for thought there. What else? Carboxylic acids, are they acids? Heck yeah. Are they strong acids? Heck no. Okay, so they're acids, but they're not strong acids like HCl and HBr and HI, but they're weak acids. So if we take a carboxylic acid and put it in sodium hydroxide, it's going to deprotonate it completely. Why? Because the pK of a carboxylic acid is around 5, and the pK of water is about 16 or 15.7. And so the equilibrium is going to lie hard to the side of the conjugate acid here. And so if you're wondering, well, how do I name a carboxylate salt? So you can see that that's covered next. You have to know how to name this kind of thing, okay? So here's what you do. You start by naming the cation. So in this case, it would be sodium, right? Sodium would be the first thing. And then you replace the name of uh, the carboxylic acid. You replace ic acid with 8, okay? Or oic acid with O8. Okay, either way you can think about it, you're still going to get the right answer, right? So let's say you had something like benzoic acid, you get sodium benzoate. If it was a potassium ion here, it would be potassium benzoate. So let's try one here. Let's say you had something like, I'll just zoom in here. And let's say we had something like this. We had propanoic acid, right? But then we make propanoate like that. So let's say you had this compound here, okay, or this salt. Okay, this would be potassium propanoate, or if you use the common, it would be potassium propionate. Okay, either one would be acceptable, but that's how you name the salt of a carboxylic acid. So you name the cation first, and then you replace the suffix with 8 or O8. Okay, so ic acid with 8 or oic acid with O8. All right, so let's see here. In a carboxylic acid in water, what's going to happen with it? Well, a carboxylic acid, when you put it in water, it's only going to dissociate slightly. If you remember acetic acid, that only dissociates about 5%, right? And so if we look at the pKa's here, this is our acid, right? This is our base. This is our conjugate base. And this is our conjugate acid. And so if we evaluate the pKa's, our acid here has a pK of around 5, and this acid has a pK of around negative 1.7. And so the equilibrium is going to lie to this side, to the side of the reactant. So again, when you put a carboxylic acid in water, it only dissociates slightly. Okay, that's a question that I ask in a pre-lab in one of the nursing labs is, how do you define a weak electrolyte? It's something that dissociates slightly. So a carboxylic acid would be considered a weak electrolyte, whereas sulfuric acid would be considered a strong electrolyte, right? Because it dissociates completely. Now, you've probably remembered this just by my scribbling here, that the pK of most carboxylic acids is in the neighborhood of 4 and 5, somewhere around there. Of course, we can mitigate or affect that pKa by adding electron withdrawing groups by an inductive effect. And we'll talk more about that later on. But again, if you compare a carboxylic acid like benzoic acid or acetic acid to sulfuric acid or sulfuric acid or hydrochloric acid, these are two completely different things, right? These are very, very, very strong acids. This has a pK of minus 7, and this has a pK of -9. Okay, we're talking about a pK of 5. So we're talking about 10 to the power of, like 14 log units difference in relative acidity. Now, if you compare the pKa of a carboxylic acid to an alcohol, you guys remember this concept from back in the day? Aereo? Anybody remember? Any thumbs up for Aereo? And you're like, yes, I loved her in The Little Mermaid. Aereo was great. No, it's something completely different, right? If we look at, the negative charge, after you lose a proton here, you end up with a carboxylate. And if you lose a proton here, you end up with an oxide. Well, you can't use atom, right? But you can use resonance. And this has no resonance forms. The oxide has no resonance forms. But we know that the carboxylate has a total of 2 contributors to the resonance hybrid. And since it's more stable, it's a weaker base, that means its acid, its corresponding conjugate acid is a stronger acid. So that's how you differentiate the relative pKa of an alcohol and a carboxylic acid. Now, like I told you before, if we go back to the old Aereo, so Aereo, okay, I said you can affect the acidity of a carboxylic acid. You can mitigate it with an inductive group or an inductive effect. So you see here that as we add electron withdrawing atoms like a chlorine, we see that the pKa decreases and decreases, right? Because of the inductive effect, right, of pulling electron density away from the carboxyl. Also, that effect is only seen on alpha and beta carbons. So we see it affected on the alpha carbon in all of the examples here, right? This is an alpha carbon, this is an alpha carbon, right? This is an alpha carbon. But it is also, it does have an effect on a beta carbon. But once you get to a gamma carbon, it has no effect. You can just assume it has no effect in this class. What else? If we have a benzoic acid derivative, right? This is benzoic acid right here. If you have an R group that's just a hydrogen, this is benzoic acid. Well, if you add an electron withdrawing group, like a nitro group or a carbonyl or a halogen, these are all electron withdrawing groups, right? They're going to serve to stabilize the conjugate base, and therefore these are going to be stronger acids than benzoic acid. And of course, if you put an electron donating group, like a methyl group or a phenol, so these would be electron donating groups, they're going to have the opposite effect. All right, so let's move on from there. And it says here, rank each set of compounds in order of increasing acidity. So there's two questions on here. Let's just put a line here. And what we'll do is we'll draw each one of these compounds out. So the first one is 2,4-dichlorobutyric acid. So let's scribble this guy out here. So this is butyric acid. So we've got 2,4-dichlorobutyric acid. The next one we've got 2,3. So that's going to look like this. We've got 2,3-dichlorobutyric acid, and the last one is 3,4-dimethyl. So if we put this here, this, and we'll just that's 1, 2, 3. I think that's a mistake. 3, 4. That doesn't make any sense. This should say chloro. I don't know if I wrote that down. But so let's just, let's fix this thing. Let's try it this way. This would be more challenging and more interesting. 3, 2, 4. I've got my chlorine in the wrong spot. Okay, so 3, 4 would be this. There we go, Mr. Dion. Now you've got it. Good. Okay. So if I look at these three compounds, which one would be the most acidic? So if I call this one, I'll call this one A, I'll call this one B, and I'll call this one C. So we'll go most acidic to least acidic. Which one of these would be most? Anybody? It's going to be B. Yes, B would be the most acidic, right? Because you've got the electron withdrawing groups closest to the carboxyl. Man, what's up with this? I can't make it. That's even uglier. There we go. Which one of these would be the least acidic? I'd say it would be the last one, C, right? Because the electron withdrawing groups are the furthest away. So then we'll put A somewhere here in the middle. All right. What the heck? Okay. The next one is kind of interesting. All right, this is actually kind of a tricky one. Which one of these, so if we go most acidic, so if we could, we'll just rank them most acidic, we'll make 1 the most acidic and 5 the least acidic. If I look at all of these, right, this is an electron withdrawing group. It's also electron donating. No, electron withdrawing groups decrease the pKa, right? They make a stronger acid because they stabilize the conjugate base, right? If you take, let's say you have trifluoroacetic acid or one of these guys, right? When you have the negative charge here and you have a chlorine, okay, something like this, right? These have an inductive effect going this way, right? And that's pulling electron density away from here. That stabilizes the conjugate base. So the more stable the conjugate base, the stronger the acid. Does that make sense? Okay. All right. So let's go back to this problem here. So we said the bromine is an electron withdrawing group. Then nitro, let me use my blue pen here. Nitro is an electron withdrawing group. A phenol, or sorry, an ether, that's an electron donating group. Then here we have an electron donating group. Then here we have an electron withdrawing group. Which one of these is the strongest deactivator? Right, the nitro group is the strongest deactivator. It's the most electron withdrawing group on here. So it's going to make the most acidic carboxylic acid here. Right now, if we look at the other two electron withdrawing groups, the one and the two ends here, which one of these is going to be more electron withdrawing? Would it be the carbonyl or the bromine? Going back to chapter 18, it's going to be the carbonyl, right, Deanna? Because this can remove electron density via resonance, whereas a bromine can't do that. Okay, it can only donate it by resonance. And so this would be 2, this would be 3. Then if I look at the two electron donating groups, well, the one that can donate electron density the most would be this one, the methoxy, right? Because it's got 2 lone pairs. And so it would be ranked in that order. All right. Well, before we take another break, I want to go through section 20.4. And I have some good news for you, and that is we don't have to spend a ton of time on section 20.4. Why? Because it's all material that was covered. Covered in earlier chapters. All right, so let's take a little review here. And these are just different ways that we've seen to make carboxylic acids already. So let's go over them. The first one is an oxidative cleavage of an alkyne that was covered in section 9.9. So we said that if you take an alkyne and you do a nose analysis and then treat it with treat it with water, that will give you 2 carboxylic acids. We also said you can oxidize a primary alcohol with the Jones reagent. And so I told you that this is called the Jones oxidation. Anyhow, the name isn't even in the textbook, but that's what it's called. Then we looked at benzylic oxidation. So benzylic oxidation is another one. So if you have any kind of benzylic proton, that can be oxidized to a carboxylic acid. So those are 3 methods of making carboxylic acids that we've already covered. Another one that you've seen already was the hydrolysis of a nitrile. If you remember, we saw this when we took the cyanohydrin. If you remember, we took a cyanohydrin, right, like this, okay, and then we treated that with H3O plus and heat. Okay, this was in chapter 19. We ended up with this where we have a hydroxyl and then a carboxyl group. Okay, so that was chapter 19. And so now it's back, all right? So if you take a nitrile and treat it with aqueous acid and just cook it up, that makes a carboxylic acid. And there's a mechanism for this. It's shown in the textbook. And we'll take a look at it, probably not today. We'll see if we get that far or not. And so what's cool about this is you should remember that you can make a nitrile from a cyanide, right? This can be made from an alkyl halide and a cyanide ion. And you see that right down here at the bottom of the page. If we take this compound, this is called benzyl bromide. And if you treat that with sodium cyanide, okay, that's going to do an SN2 reaction, right? And then we have the nitrile, and we can just hydrolyze that with aqueous acid, and there you go. You've made yourself a carboxylic acid, and you've made a carbon-carbon bond, which is kind of neat. Now, this is a reaction that we haven't looked at yet, but once you see it, you can just say, well, this makes total sense. And this is a way to make a carboxylic acid from a Grignard. So if you take a Grignard reagent, so let's say you have Rx, and you treat it with magnesium, okay, then you get the Grignard. So this is your Grignard reagent, okay? If you take a Grignard reagent and you react it with CO2, so this is like dry ice, okay, which is just carbon dioxide in the solid phase, right? This is a powerful nucleophile, and carbon dioxide is a great electrophile. And so it's going to react with the carbon dioxide to make a carboxylate, and then you just treat it with aqueous acid and it protonates to give you the carboxylic acid. So this is a total of 2 steps. One, after you've made, we'll say, magnesium to make the Grignard. 2, hit it with carbon dioxide. It doesn't matter if it's in the solid phase. It could be the gas. And then number 3 is treat it with H3O plus, and that's a way to make a carboxylic acid using Grignard chemistry. So now we've got a new method to convert an alkyl halide into a carboxylic acid. We can use the nitrile method by using sodium cyanide, and we can also use the Grignard method, which I have shown here. So again, this is kind of the Grignard pathway towards making a carboxylic acid. It's pretty ingenious when you think about it, just using carbon dioxide. If you're wondering, has anybody ever seen dry ice like this before? I don't think we've used this in the lab in 3102 in a while, right? Anyhow, one of my students asked me, like, where do you get this? You can actually buy it at King Supers, believe it or not. They have it usually by the exit. There's a little cooler there that's got dry ice in it. I'm not sure what people buy it for, but you can buy it if you need it. All right. You're like, I'm going to get some dry ice this weekend. Anyhow, so let's see here. Identify the reagents that you would use to perform the following reactions. So let's try a couple here. That'll take us to section 20.5. Just a couple of quick reactions here. Nothing really new under the sun. This is kind of review. So if we take ethanol and we want to make acetic acid, what do we get? The first thing that comes to my mind is the Jones oxidation. So you could use sodium dichromate, sulfuric acid, in water. That's one way. Or, and I think Audrey brought this, no, maybe not. Maybe we weren't talking about benzylic oxidation, but you can also do it in base. You can use potassium permanganate, right, to do a benzylic oxidation in water and just cook that up. And then in the second step, you end up with a carboxylate, so you have to acidify. So that would work. The next one is taking toluene, which is methylbenzene, toluene, and converting that to benzoic acid, and that's just a benzylic oxidation. And so if we want to do a benzylic oxidation, the best method to do that is just a Jones oxidation. So we'll throw that in here, sulfuric acid, water with our sodium dichromate. The next one is benzene to benzoic acid. This one's going to be a little more interesting, right? But if we take benzene and we convert it to bromobenzene using bromine and iron 3 bromide, then we could use the Grignard pathway, couldn't we? Right? We would treat this. Oops, where's my bromine? Where's my money? Where's my bromine? Anyhow, so then we could treat it with magnesium followed by carbon dioxide. That's going to give us the carboxylate, right? Which we're not going to isolate. That's just going to be in situ. And then, of course, you can acidify that with H3O plus, and that's going to give you benzoic acid. Is there enough space to do the last one? The last one is 1-bromobutane to pentanoic acid. So if you had 1-bromobutane, so that's this compound, and you want to make pentanoic acid, so 1, 2, 3, 4, 5. So for this, you could use sodium cyanide. So just treat it with sodium cyanide, and that would make this compound. And then all you have to do is hydrolyze it, right? So you'd use H3O plus and heat it. You could also do this. You could make this using the Grignard method too. So I'll put here or, since I'm running out of space here, I'll put or Grignard method. That would work too. There's nothing wrong with that. That would totally work. So yeah, either one of those methods to go from 1-bromobutane to pentanoic acid. So that covers the first 4 sections of the chapter. And now we're going to take a short break before we get into section 20.5, where we start to look at new reactions of carboxylic acid. So I think it's good to take a little or a deep breath before we start tackling some new reactions. And then we're going to look at some nomenclature of esters and amides and some other things. And we want to make sure that we get some of that nomenclature done today so we can practice that over the weekend.